designing or operating systems such that they use energy and resources sustainably. So, at a rate that does not compromise the natural environment and the future needs. So, it is the duty of all the engineering engineers and every engineering discipline that is to engage in a sustainable design by employing numerous initiatives like life cycle analysis, pollution prevention, design for the environment, and design for recycling. So, as an engineer, it is our duty to link the technical and non technical aspects in this in a global context. So, coming to sustainable energy, it is power which is able to be replenished within a human lifetime and so cause no long term damage to the environment. So, coming to this, we have to follow three main categories, that is, environmental sustainability, social sustainability, and of course, the procedure should be economic as well, that is, economical sustainability. So the fossil fuels which are we are using, that is coal, oil, and gas, which is account for about 75% of global greenhouse gas emissions and nearly 90% of all carbon dioxide emissions, which we cannot do much about it, because if we need to use a car or any public transport, we need petrol, and diesel, gas, everything. So to qualify a power as sustainable, the energy must be efficiently obtained and distributed. So, such an initiative is a renewable energy that is powering a safer future. So, renewable energy, it plays a fundamental role that is in promising derivatives. So, coming to renewable energy, we have already the solar energy, wind onshore, which has been readily available in India. So, here I will be talking about one of the most promising derivatives of renewable energy, which is offshore wind energy. So, the wind turbines, which is placed in offshore. It is an innovative technology which marks a milestone in the development of renewable energy. And we believe that this can create like huge potential. It has huge potential and derive a lot of energy, and with a so that the governments have started investing mostly into the offshore part. So coming to offshore wind energy, what is offshore wind energy? It's a source of clean and renewable energy obtained by harnessing the power of wind offshore. So the offshore, as we know that we have like more wind available, so it can reach a higher and more constant speed due to lack of barriers, then high potential and strategic added value, both at social, economic, and environmental level. So this is one of the renewable source that will play a crucial role in the decarbonization process. Offshore wind turbines, which is in onshore, can produce about 2-3 megawatt of electricity, but the offshore wind turbines are much larger in size and it can produce up to 8 to 14 megawatt per turbine. So this causes less impact on people and landscape. That is the most important part, because we already have India in parts of Tamil Nadu, Maharashtra, and Rajasthan. We have different onshore wind turbines. So the main problem that is happening to the environment is that it affects the people living around. That if it's densely populated, and also it affects the landscape. So these disadvantages in the onshore wind, we can eliminate that with the offshore wind turbines. But the problem comes in the economic part, that is the cost per megawatt for offshore wind turbines are higher, because we need stronger structures that goes into the sea, and the foundations which is needed in the marine environment, it requires like a higher quality than that of the going into the land. But however, the disable tariffs can be achieved on account of higher efficiencies of these turbines. So here, when we come to renewable energy, the offshore wind farms are continuing its growth. So mainly the Scandinavian countries like Norway, Denmark, they have started the journey in late 90s, and they have like fixed wind farms. That is, they have created the wind farms which the electricity has been generated. And then China, it come into forefront, and it is investing a huge amount of money on offshore wind farms so that to get sustainable power. And other countries like UK, they are planning to change the cars from the petrol and diesel by 2030 to electricity, and the new homes will have heating system which is will depend purely on electricity rather than the gas which is being used now. So coming to renewable energy, we know there's geothermal, hydro, solar, wind, and wind offshore and wind onshore. So this graph shows that how the spending has been done, that is in different countries. The solar power, especially in Central America and Asia, we are giving more investment to the solar power. and the wind offshore onshore as well, and then wind offshore is also been taking place. So considering to the fossil fuels, the starting, we have to put a lot of investment to the industry then for its growth, but we assume that after the first investment are going to get a very good investment and good sustainable power from these sources. So this is how the wind energy offshore is going to function. We can see this is some of the offshore wind turbines. And this wind turbines, this energy will be taken from the force of the wind out at the sea, and it will be transformed to the electricity by rotation of these wind turbines. And the electricity will supply to electricity network onshore. This is onshore. From that, we can distribute it. So this is done by using undersea cables, which is very important. So this cable will go from the platform to the onshore grid. That is mainly through underground. That is electricity produced by the offshore wind turbines. It travels back to land through a series of cable system that are buried in the seafloor. So such buried cables, they are common. The techniques we are using it for the oil and gas, for transferring petroleum gas. We have like the technology for undersea cables. So that is adapted here for the offshore wind energy farms. And as a civil engineer, I have least concern about the. I am not very sure about what's happening in the onshore side. But as a civil engineer, we will be concerned about what kind of structures will be constructed offshore for the wind energy farms. So coming to this, we can see this is the wind energy farm. So how we'll fix it in the water, that is the main concern. So here we can use it up to height, up to water depth of 1,000 meter it can go. So this is how the structure is coming with respect to the water depth. So at the lower water depth, like 20, 30, up to 50, we can use fixed structures. So this is a monopile structure. So this monopile will have a pile which will go deep into the marine environment. It's depend upon the site condition. If the site uh, condition, that is the if the geotechnical part, when we consider if we need more strength, then the pile has to be designed appropriately. So the monopile structure, it will carry the wind offshore turbine like this. So this the main concern is that the turbine when it works, it should not move. So we will be mainly concentrating on how these structures can be built so that there is very least movement which has happened to the wind turbine, and the wind turbine can function efficiently. As you can see, when it goes to deeper, we need jacket like platforms which requires a lot of steel, and also the piling which is going. So a lot of materials will be needed, which make it very expensive. Then again, when going to the deep waters, like above 200 meter, 300 meter to 1,000 meters, we can adapt floating offshore wind energy platforms. So the main studies and investments are now carrying out in the offshore floating platforms. So as the based on Archimedes principle, we already know how to float a structure in the water. So this is called a tension leg platform. So this platform, it can float in water because we can adjust the buoyancy by giving more weight underneath. So once it floats, then it is fixed to the seabed using tethers. This is also called anchors or mooring lines. So this is called tension leg platform because it is tethered, that is with tension, and then fixed to the seabed. So here we need less material. We can use this into very deep offshore as well. So this is another platform which is called a semi-submersible. So having the same concept, but here the mooring lines or the anchors is going to be have a catenary profile. So we have to properly model these anchoring lines, that is how the force will be transmitted from this to here, because this is a huge mass that we are carrying here, and also this is sea, it will be also affected with extreme events. So in the extreme scenarios, we have to see that this anchor lines or the mooring lines does not break and take away the platform. And then this is spar platform. This is similar kind, which is already been built in the Scotland High Wind, and have adapted this one. So but this requires more material than the semi submersible and tension platform. So now the studies are more concerned with this too than how it will be adapted to a particular area, because when it comes to the North Sea and if it goes back to the Indian Ocean or like Bay of Bengal, the site conditions differs, and also the environmental parameters there, that the wind conditions, the wave height, wave conditions, everything differs. So we have to choose the platform with respect to the site conditions. So coming to the structural part, this is a monopile structure. So this is an interdisciplinary design, because there will be aerodynamics comes to part, which I am not much aware of. Then comes the hydrodynamics part, that is including the wave part, and then the geotechnical part where we have to model the stiffness of the pile, stiffness and damping of the pile. So here, when coming to the hydrodynamic part, we have waves that will be acting. So in a structure which is in the onshore, that is, if you are having a 10-story building, maybe if its height is like about 50 meter, so it is a huge building. So here the main concern is that that much. Even in this figure it shows little, but here there can be 30 meter to 50 meter, and that part we have to consider the wave loading. Also, there is a wind loading. So when we consider the wind factor for huge buildings, we have to consider the wave which will induce more forces on the structure. So with respect to wind, we also have currents. So the currents will be acting like a 1.6 to 2 meter per second in the water, and this will, if the wind is in the direction of the waves, so the waves and currents are in the same direction, then it will increase the wave height and increase the load. And if it is in the opposite direction, it will reduce the wave height. So these all factors, these loads, that is respective of the wind load, we have the wave load, we have the current load, and these all have to be considered for calculating the forces on the structure. So when designing the structure, we this is how we consider the free body diagram, the damping, the mass, and we have to calculate the natural frequency of the system, and how it behaves in different modes, that is different mode shapes. And when the natural frequency of the system, if it matches with the frequency of the wave, then definitely when both frequencies match together, there is resonance, which will cause the vibration of the structure, which should not happen. So these all are the design features which we have to take on care. So as I said, soil effects, which include the stiffness and damping, there are different finite element models for designing the turbine, and also for designing the piles. The site characteristics is one of the important. Well, we design, that is a wind speed at the reference height. So reference height is this one, that is at the hub. So this can be 50 meter. If 50 meter gives a very good wind, like 8 meter per second, that is good consistent wind, then we can design our platform height to be 50 meter. And if it is 100 meter, we are getting very consistent wind, then we can increase it to 100 meter. So the not only the wind speed, but the consistency of the wind is also important in when we are selecting a site. Then coming to the water depth, wave height, wave pinit, so these all are site specific and has to be calculated depending upon the site where we are going to um, build the platform. Then coming to the turbine characteristics, the rated power, rated wind speed, rotor diameter, cut-in, cut-out speed, mass of the rotor nacelle assembly. These are some other turbine characteristics. And the ground profile, where the soil stiffness variation with the depth and soil stiffness one diameter depth. So we have the PY curves and TZ curves to calculate the stiffness and damping of the piles. And then coming to the floating offshore wind energy farms. So floating offshore wind energy, as I said, the main advantage will be less material. So based on floating structures, open the door to site further offshore. So when we go further offshore, the wind there is more. So we can utilize more wind power to generate electricity by allowing the deployment of wind turbines in larger and deeper offshore areas with high wind potential. So the megawatt of electricity which is generated, it can increase, like from if it is 8, then we can increase it to 15 megawatts, that means go to offshore. This overcomes a stumbling block to providing clean, inexhaustible, and non-polluting energy for a more sustainable planet, and potentially low environmental impact, and the ease of manufacture and installation. So the ease, what we say, platform is already floating in the water, so we can actually install it in the assembled it on the land, and can be towed using any barge to the location. So we can take advantage of the strong winds blowing in the deeper areas and improves the energy efficiency. But as we said, it is a very interdisciplinary area where the aerodynamics part has to be properly concerned, and we are as a fluid structure interaction is another important thing. So this shows the current profile. So current is like will be higher at the top and then coming down, and then this is the wave. So the wave force, it is like an ellipse. So the wave velocity distribution is like an ellipse which will be higher and then coming reducing into the bottom. And then there is a tidal current and the tidal elevation. That is when the tide comes, it increases and decreases. Wave current loading, and this is the wind loading. So all these features has to be taken into consideration. And then the main thing is the mooring lines. The mooring lines should be such that it should keep the structure at position while working. That is a station keeping system. So this is stabilized by moorings and anchors, and design distributes the masses and weights properly. So the another important things are the manufacturing facilities nearby the site, the availability and price of materials and equipment. So these are economic factors which will add up to the design. So next is another thing which we are concerned, that is 80% of the offshore wind energy platforms fails due to power cables. So as I said, that is the electricity generated from an offshore turbine. This has to be transmitted to the onshore grid. So how we going to transmit? That is using a power cable. So this power cable, we can see this is being connected to this platform, and this comes like this shape, and then it will go, under the seabed. So under the seabed, it will go up to the onshore grid. But there is a portion which will stand in the wave. So this length, which is standing on this wave, is the main concern, because this will be affected with the dynamic load. That is, waves and currents will be acting on this portion of the cable, which make it a it's a dangerous design concept that will come here. So this will be subjected to all the loads, and it will vary, and this is the main part which will cause the um, failure of the offshore wind platform. So if I say that you might have seen that this cable is having like a very different shape. So this shape is called lazy wave configuration. We can just hang this in a catenary mode, which has already been done. So catenary mode, what happens is that if the top platform has any movement, that will be directly transferred, and this cable will come out. That is, come out from the touchdown zone. That is where it is touching the sea. It will just pull off from there. So that is one big concern of failure. So in order to overcome that, instead of a catenary profile, we are bringing the cable, and we use buoyancy chambers. So this is something which will cover the cable at some location. So these chambers have high buoyancy. So this will pull the cable like this and give a lazy wave configuration. This configuration is called lazy wave. So what will this will help to decouple the motion of this platform from the touchdown zone. So our touchdown zone is saved. That is, the platform, all the platform motions will not come into the touchdown zone, because it can decouple that movement from there to here. So this buoyancy modules and lazy wave configuration has helped a lot. That is for the power cables. So if you see that how a power cable looks like, this is very complicated, because it should have like it is not a homogeneous material. We know that when it is a homogeneous material, it's easier to find out the axial stiffness, the bending stiffness, and for the design. But it is a very flexible structure. So design of flexible structure is very difficult. And on the top of that, it has the copper, aluminum, and also this even though this electricity is going through this, because so that it needs a very good protection. There should not be any water ingress. So it has all the protection covers. That is, it is armored, and it have a polyethylene cover. So it is a combination of different materials: aluminum, copper, steel, polyethylene, all this. So the modeling and finding the properties of this cable is difficult, and the forces which is acting on the cable, that is something important in the design of the offshore wind energy platforms. So these are some cable failure modes. As we know, that is, it is a not a homogeneous material. So mainly the tension will be taken by the inside material, and the bending, that is, if over bending happens, the outside material will break first. And again, there is a dynamic load which is given by the waves, so that will cause fatigue. So fatigue is small crack because of the waves which has been always acting on the flexible body. There can be cracks which cause fatigue, and fatigue will this cracks which is caused by the fatigue will expand and then cause water ingress, and all the can eventually lead to the failure of the cable. And also there is impact from animals. So as I said, it is like sustainable. The what the how this is going to impact the marine life, that is another part of the study which is going on. So that is also important, because wind energy farms, how it impacts the marine life is another study. So the main failure of this power cables, it happens because of the currents. So currents are, the waves are mainly happening on the top, and the currents will be gradually we have seen the current profile which will be larger and will have a like a decrease to the bottom. So when these currents are acting, so what happens, velocity reduces and the flow suppression occurs when it reaches the cable, and then there's vortices. This we might have studied, that is how vortex induced vibration occurs. So this vortex induced, this vortices will start to grow and grow and will induce vibration. So because of this vortices and a reduced velocity near to the cable, this cable will start to vibrate. It can vibrate in both direction, inline direction, and it will vibrate in the other direction also. So as the velocity will be higher here, less here, and it will be different velocities throughout the length of this because the length is large, because we are talking about a water depth of 500 meter. So at every portion, there will be different modes of vibration, which is called the multi-mode vibration. That is causing the structural motion. So this will vibrate in different modes and different shape, which will eventually break it from the hang off point. So that is how the failure happens in case of vortex induced vibrational cables. So the current flow, the top end motion, along with this is the main reason of failure. And the curved slender structures in deep water will subjected to fatigue because of these movements. And multi-frequency response. So as we know, this have a that is the water shedding will have a water shedding frequency. If the water shedding frequency matches with the natural frequency of this cable, then it will resonate. The lock-in condition happens and the resonance will come. So this will definitely lead to failure. So this is how the vortex induced vibration on cables. So coming to this, as I said, when the vortex induced vibration, so we can see how the vortices are going from the flexible cable, and this will leads to, if this matches, this frequency matches with the natural frequency, then it will result in lock-in. The long cylinders can have multiple locations where the frequencies synchronize along the length of the member. So this is how the mode shapes varies along with the length of the member. So we can see that the cable like move like eight like figure. So it is going crazy. Actually, that is going to and fro in cycling motion. Eight like figure mean it is going, like this. So this will definitely break it from the hang off point. So the dynamic forces produce cyclic motion of the cable, and a sharp transition in the cable stiffness causes failure at the rigid connection point. And the repetition of the foregoing process and the overbending, it can also lead to the fatigue damage of the cable. So this is a main concern which has to be taken care while designing. So as we see, this is a combination of like fluid and the structure. So fluid mechanics and structural mechanics. So first of all, while coming to the fluid part, we have the Reynolds number, which will depend upon the velocity of the currents and also the diameter of the member. So as I showed the power cables, the diameter of the power cable is like 300 mm to 500 mm. And then coming to the reduced velocity, then the forces will be acting on the two directions. As I said, it will vibrate in both direction. There is lift force, that is uplift force, and then there is a drag force. So these forces and the displacements that will happen, so this all has to be figured out, and we have to see that what frequencies will come and act on the structure and how we can sort it out. So along with this, that is the Reynolds number, the Stroll number is nothing but the water shedding frequency. It will give the water shedding frequency, and then the normalized velocity which will be acting on the cable, and damping. Damping is another important. There is two damping: structural damping and the hydrodynamic damping. So two. This is the total damping will be a combination of structural and hydrodynamic damping, and then reduced damping. Then the other three properties, that is the natural frequency of the structure, the axial stiffness, and the bending stiffness. So these also comes into picture, and we have to see how this stiffness has to be managed, and how in such a wave condition. So we have different numerical models for the study. So as I said, it is an interdisciplinary area. We have different softwares which will handle the top part, that is the offshore wind turbine. So there are also open source softwares like Open Fast which can do that. Of course, ANSYS, it has different modules like the Fluent, the Aqua. So this can do different um, parts of the platform. So fluid structure interaction, that is the area which will be inside the water, that can be also handled with the fluent. That is the structure movement can be transferred to the fluid, and the fluid movement will be transferred to the structure. So this numerical model is a representation of the real by mathematical formulation. So it can be analyzed by computational methods, the finite element method and finite volume method, which is generally used in the area. And here we have another concern, that is we have water and air. So we have to model the water and air. So that air water interface modeling is also an important thing which will come into the fluid structure interaction study. But before that, these two softwares like OrcaFlex and Shear7, this is mainly for studying vortex induced vibration and for cables. Even OrcaFlex is being used by the industry. It is a commercial software, but it does not actually model the different materials which will coming on the cable, but it induces some factors like for the considering the uh, different materials which is going to the cable. So it is non-homogeneous, but it considers a homogeneous and then give a factor to adapt to that is it is taking different materials. So before, even though the softwares are available, it is always important that we have to carry out experimental investigation to study the behavior of these cables. So, but to study the behavior of the cables by experimental investigation, I meant that we have to scale down the larger one. So if we have wave tanks to do that. So in the wave tanks, if we have to scale down using fruit scale, we'll scale down the properties. But the main concern here comes that when a small scale model is used to study the behavior of a prototype, then it should reach a certain degree of possible dynamic similarity. So there is design of the reduced model. It should at least grant the global static geometric configuration, the global dynamics, the local dynamics. By the global dynamics, I mean the natural frequency has to be similar, and the mode, that is the different modes it will vibrate. So the mode shapes also we have to, if we have the mode shapes available in the scaled one, it will be possible to make it to the prototype. The small scale model to preserve the structural parameters, that is important, which is bending, axial stiffness and mass ratio. So if bending and axial stiffness is like we are able to preserve that, then of course we can attain the similarities in global dynamics, that is by natural frequency and the mode shapes. So here, when we are going to first model, the food scale was adapted for the floating unit, causing the top motion. But the problem is that when we have a water depth of 2 meter, 3 meter, which we can create, if we fruit scale the top one, which that we can use a scale of 1:50, but if we use the fruit scale for just taking out the diameter of the cable, so it is 300 mm. So if we scale down to 50, then it is like less than 10 mm, that is maybe 5 mm. So if we the model that 5 mm, that is a very small diameter, and try to study the different mode shapes and frequencies, then it is not possible because it cannot represent the global dynamics. So the main concern when coming to an experimental study is that we have to model it such that we need to get a higher Reynolds number. In the real scenario, the Reynolds number will be in the order of 10 raised to 5. But when we have a small diameter cable, then the Reynolds number, which depend on both the velocity and the diameter, will be very small in the range below 1000. So the main concern with the experimental investigation will be matching a fruits and Reynolds similarity. That is a distorted scale we have to adapt. That is, it can that is at this concomitant means at the same time we should have both the fruit and Reynolds similarity. So we have different so once the experiment is done, so this is one example. We can set up this is just a catenary profile. The lazy wave configuration has not been studied in the experiments. This has been carried out. One or two studies are there, but we have to carry out studies. So in these studies we have accelerometers which will measure the accelerations. So this we can convert to the displacement. So we can see know that with a particular current range what will be the movement of the cable, that is in both direction. So we can find out the displacement, and from that we can find out the forces. Then we can find out like in which modes it is giving higher vibrations, and what will be the largest forces we are getting, that is the drag force and lift force. And by different experimental studies we can calculate the drag coefficient and the lift coefficient, which we can use in the theoretical formulations. So this is how the results have come up. So see, the this is how the behavior happens, that is when the velocity range is increased. So that is the velocity, the current velocity we increase, then we can see at some points this is how the cables behave. That is figure 8 like motion. So that is definitely going to break it from the hang of point. So we have to find, that is the what is the natural frequency, what is the vortex shedding frequency which is happening, and how these vibrations are going to affect the cable. We can also use the strain gauges so that we can find the bending strain in this direction and this direction. So the bending strains of the cables can be found out from using strain gauges. And this is a study where all there is the effect of the soil is also considered. As I said, the seabed characteristics, if it is a soil like clay, or if it is depending upon the character of the soil, how this touchdown zone will behave. That is one of the study which has been carried out in different current conditions. And this is one of the experimental investigation which has been carried out. So this is like a setup made so that the diameter will be big, so that we can attain the Reynolds number. That is here a Reynolds number up to 70 × 10⁴ was attained because of increasing the diameter. But the axial stiffness, bending stiffness, and mass ratio, these three properties will be kept similar to the prototype, so that the dynamic motions we can get a quasi similar movement. This is how the deflected shapes is going to behave. So this is with respect to different velocities. So this is the vertical length. So in vertical length, when the small currents are acting, this is just vibrating, and then it is vibrating in figure 8 like motion. That is, we can see that with respect to the vertical height, the different areas, that is the multi mode vibrations, different areas give different kind of deflections. And this is the vortex shedding frequency with respect to the natural frequency. So once we know the vortex shedding frequency of a particular dimensions, that is the stiffness and how it is behaving, then we can make the natural frequency that is away from the vortex shedding frequency. So this is the mode shapes. So in this experiment, the mode shapes are like measured at a very very short velocities, that is at distant velocities it is measured, so that we can see that from one mode shape to another mode shape, when it change, how the amplitude is increasing. This up to 7 mode shapes are created. And then finally the drag coefficients are measured and codified. So this drag coefficient which will help us to use the theoretical formulation and find the forces. So this is a demonstration of a flow wave. This is this is a facility which is a commercial facility which is available at the University of Edinburgh, where I will be doing experiments. So this is a 12-meter diameter large tank. So this tank has 128 wave makers around it, and this will can generate a random sea, a three-dimensional condition, like currents. It can generate waves, currents, and so that we can properly test the forces which is acting on the cable. So we can have the waves generated, currents generated, then the forces, the bending strain, and everything can be recorded. So this facility also have an underwater collision camera. So underwater camera can easily we will give some reflective markers, so underwater cameras can record the displacements. So like that we can get the displacement in different directions. And then the next idea is using VAV suppressors, so that the vortices will not be formed around the structure, but it will be like the vortices will die out because of this helical streaks. So this helical strakes design will help to reduce the vortex induced vibrations. But the problem is that the height of this and the diameter of this helical strakes has to be properly designed. Otherwise, it will increase the drag force, and this will eventually cause the fatigue. So the one of the solutions is adapting helical strakes, and there are different solutions people are trying out, that is covering the cables with some like material which is moving, so that there will not be any marine fouling, and also because of the movement the vortices will not be generated. So mainly the vortices will generate and the vortices will increase and the vibration occurs when the surface is smooth. So we are trying to make some arrangements so that the surface of the cable is not smooth, and so that the vortices will be decoupled from the structure, and the forces and the vibrations can be reduced. This is how an offshore wind farm should look like. So when coming to the UK, we can see that from the flight itself, that is there are so much of fixed platforms, which is that is farms which has already been adapted in the area which is in the near the North Sea. So this is the to just see how the shape will be. It currently the offshore wind provides just 0.3% of the global power generation, but its potential is very vast. Much works need to be done by the government and industry, and they are doing it. Much investment is going to the offshore, and even in India, for so that we can move to a mainstay of clean energy transition. So India is blessed with about 7,500 kilometer of coastline, so we can definitely have offshore wind energy. But the thing is that we have to see that how the wave characteristics, the site condition, how where the wind will be available. So these are some of the things which we need to see. So the Ministry of New and Renewable Energy, that is MNRE, it has considered offshore wind as one of the recognized offshore wind as a renewable energy source. That is in 2000, maybe 2 3 years back. And there is a lot of studies which is happening. So the National Institute of Wind Energy, it provides data. We can see that is in this area near to Tamil Nadu and Gujarat, there is a large potential, whereas a consistent wind above 6 meter per second is readily available. And here above 8 greater than 8% is also available in the areas near Tamil Nadu, where we have huge potential for offshore wind. So the Danish government and the government of India has taken up action, and they have done a site survey and located about 15 locations, that is near to Tamil Nadu and also near to Gujarat. And this 15 location itself can give about like more than 50 gigawatts of electricity can provide. So the site studies are done, and the consistency of the wind and the height at which the wind is readily available, all this has been found out, and the wind farm locations has been found. And many investment has been going, and by 2030 we are trying to get a more result in this field. So coming to the conclusion, that is offshore wind identifies sustainable renewable energy source for power generation, and it can provide environmental sustainability, social sustainability, and economic sustainability. And the identifying location for offshore fixed and floating platforms, and it has very low environmental impact, and we can have clean, inaccessible, and non-polluting energy for a more sustainable planet. So thank you. I can just show that is how the this is the demonstration of the experimental facility where we can generate the waves and currents. I hope it's this.
Thank you, ma'am, for the wonderful section.
Okay, so this is how the
Please
waves
fill
will be
the feedback
generated.
on
Yeah, we could just
put in the and put it in the chat box. Thank you,
yeah,
ma'am.
1 second.
Thank you, ma'am. Once again, thank you.
Okay. Yeah. Any questions? Yeah. Thank you.
Dear participants, please fill the feedback form put in the chat box. And you can leave the session.